thank you, and thank the organizers for inviting me here and learning about all this new BA chemistry. So this first session is about aptamers, and my lab does not do too much of therapeutics. So I will share with you the only thing we do first, deliver to the eye. Right? So we usually use eye drops, and we want to have the eye drop probably stay on the surface line of the eye for a longer time. Right? So we just have this simple idea of obtaining some aptamers that can bind to the surface of the eye, and then you conjugate that to the surface of the liposomes, and you load drug inside liposomes, and that hopefully can retain the drug for a longer time. So we got this selection process by buying some eyeballs, pig eyeballs from a slaughterhouse, and then peel off the corneal layer and use that as a target to do the selection. And it's actually not too difficult because the surface eye is actually quite lubricated, right? So you don't get a lot of non-specific binding. After 12 rounds of selection, we got 2 aptamers, and the affinity is not great. I think a part of the reason is this is flow cytometry based affinity measurement using a fluorophore-labeled aptamer, because we use the pig cornea to do the selection, and we use human corneal cell to do this binding assay, right? So it may not be exactly the same protein. So we get a KD of about 300 to about 200 nanomolar for the 2 different aptamers. Not as good as the isomers, but when we conjugate them to the surface of a liposome, right, using cholesterol modified aptamer, then the affinity increases a lot, right? Because you have this multivalent binding that you have to get in the avidity. So our first aptamer has KD now down to about 1 nanomolar when you measure the affinity of the entire liposome. And actually you can see, right? So we now label the liposome with a red fluorophore dye that mix them with the cornea and then wash away the free liposomes, and you can see, right, the strong fluorescence, right? So they stay on the surface of the cornea compared to our controls. So it does have good affinity and can stay on the surface of the eye for a long time. We're now doing some pull down test. We know it's a protein, right? So when you treat the corneal cells with a protease, it does not bind anymore, right? So and then we're doing some mass spec to try to figure out what's the target of this binder. Yeah, that's about the therapeutic side of what we do. Most of my lab is doing selection of small molecule binding aptamers. And I call it reselection because many of the targets we're using have been selected again, previously, right? So we'll just do it again. There are a few motivations. The one is we found the main important aptamers do not work, right? So they publish as an aptamer, but they don't bind. And now the new selection methods are available, right? So for small molecules, the traditional way is to immobilize the target molecule, but now you can immobilize libraries that allow you to select actually any molecule, right? Some molecules you just cannot immobilize. And with deep sequencing, you can get a lot more information compared to the old method, right, doing the sample sequencing. So our work in this area started with noticing this paper. They claim to have an aptamer that can bind arsenic, and this paper has been cited now probably close to 150 times. Right? So this is the African sequence they published. It's 100 nucleotide DNA, and it was obtained by immobilization of arsenic-3 and arsenic-5 on the surface. And the validation of binding was using SPR, right? Again, by using immobilized arsenic on gold surface. So this aptamer was claimed to bind to both arsenic-3 and 5 with low nanomolar affinity. Right? So when people use it to make biosensors, they can only detect arsenic-3, not arsenic-5. So how was the detection done? So this is how people usually do it is using gold nanoparticles. You've probably seen 50% of arsenic detection paper use gold nanoparticles. The idea is you mix the aptamer with arsenic, and then they're supposed to form a compact binding complex that will hide the DNA base, right? Then its adsorption to the gold nanoparticle is inhibited. So the gold is not protected by the aptamer. Therefore, when you add salt, the gold nanoparticles would aggregate and then you get blue color. So is that true, right? So we repeated the experiment, and yes, we can observe that. So when you don't add sodium chloride, right, you get red color of the gold nanoparticles. When you add sodium chloride, you can see right, arsenic 3 give you blue color, and arsenic 5 gives you red color, consistent with what literature reports. The problem is when you replace this aptamer by any other DNA, you get the same thing, right? So it's a random 13mer, exactly the same, right? So it has nothing to do with aptamer binding. So what we believe, right, is measured here is arsenic adsorption. So arsenic 3 can adsorb to the surface of gold, and that adsorption prevented the DNA from adsorption. So it does not matter if it's an aptamer or it's not an aptamer. You can prevent this adsorption, and the result is the same, right? You have no DNA protection, and you get aggregation of the gold nanoparticles when you add sodium chloride. So this experiment does not really validate aptamer binding, right? And actually, the majority of the work using this aptamer for detection is gold in one way or another. Here you see, right, SPR, that's gold. Using Raman, right, thirst, that's gold. Fluorescent quenching, that's gold. And here the color change, that's also gold. Then we went on and did a lot of the binding assays to try to see, right, if that actually is an aptamer or not. And we cannot find any evidence, right? So we did ITC, we did a fluorescent staining, and of course tried the gold. And yeah, that's, in our opinion, it's not an aptamer. And there are more excellent work to question, right, how does the aptamer work. So this paper is not from our group, it's from Caroline and the West group in Belgium. So they wrote this big Japanese paper questioning the aptamers claim to bind to ampicillin, an antibiotic compound, right? No binding, whatever. They did mass spec and more ITC. And this paper from the group in France also questioned about aptamers claim to bind to a pesticide, right? So these 4 compounds, and also claimed that these aptamers, this DNA, can bind to all of them with low nanomolar affinity. Right? So this molecule is not really that similar, right? So it's unlikely, one molecule can bind to all of them with low nanomolar affinity. We also did work on this S9-amine aptamer, if you remember, right? So that's like a pretty old paper. So that's the original sequence claimed a KD of about 10 nanomolar, and you can truncate them down to a very short sequence. You still get about 100 nanomolar affinity for S9-amine, right? Such a small molecule. I think the problem is the binding assay was performed with immobilized S9-amine, right? So when you immobilize S9-amine through the amine group, really you get like ethanol, right? So not much left. So when we did ITC, we don't see any binding. So, and here we compared 2 cortisol aptamers. So these are not selected by us, but this is an interesting comparison because these 2 aptamers were selected using a similar method. So both used the library immobilization method. The difference is if you look at the library design, the first one, published in 2014, has a hairpin in in one of the primary binding regions, right? The second one forms a hairpin by putting the 2 primary binding regions together. So one is inter, one is intra. So the first one reported a KD of about 10 micromolar, and the second one is about 100-fold better. So everyone pretty much, in the literature use this one for making cortisol sensors, and actually they don't use the full one, right? So this is ADMER. They just truncate it, remove the primary binding regions, and just leave with the random region. So when we tried, so this aptamer, right? So with this inter-parameter binding region helping, that has good binding, right? So they reported the 0.1, we got 0.25. I think it's close enough. But the other one, right? So we saw no binding. So, but unfortunately, the majority of people, right, use this aptamer to make biosensors, and we don't know if the full length can bind or not. I tend to believe, because I think they've done a lot of rigorous, right, assays, but the KB, right, is 10 micromolar region, and I think this is probably the one people should use for making biosensors. So this is aptamer for chlorphenicol. This is also a highly cyclic aptamer. The original length is 80 mer shown here, right? So everyone using this truncated by simply removing the parameter binding regions in yellow. So once you do that, right, so they believe the structures like this. So to me, right, if this one can bind, this one will not be able to bind. The structure is totally different. And when we tried it, yes, there's no binding, right? So there's just so many, I think, unbound aptamers that I think a lot of the things I showed you, right, are actually highly cited. So hundreds citations, right, using these aptamers for making biosensors. Sometimes I think that's a good explanation of like arsenic, right? So why people can observe this arsenic dependent response, right? So not because atom binding, but because of arsenic adsorption to gold. So I think we need to be very careful, right? So when selecting new aptamer, especially when truncating aptamer, ITC I think is a good method, and gold nanoparticle is not recommended. Right? So I think a group of authors, right? So I think a lot of in this conference are making this paper saying minimum aptamer publication standard, right? So you have to have the validation of the results and provide sufficient data, right? So to make sure published aptamers can be bind. Okay, so the last part I will just share with you some of the aptamers that we recently got. The traditional method, right, is to immobilize the target, right? So that's ATP. You immobilize it through a linker to an agarose bead, and that's how Jack Shostak group got this aptamer in 1995, and everyone's using that. I think now a more popular method is to immobilize the library through hybridization, right? So, and you hope your target binding can release the aptamer, and you can collect that for PCR, right? So in that case, you can use unmodified target. So we started with tetracycline antibiotic, so oxytetracycline actually. So this is not the previous recorded by immobilization of the tetracyclines, and that's the aptamers they got. I had no interest in testing them because they're too long, right? So it's not truncated, they can 80 mer long. So we did the same selection using oxytetracycline as a target, right? So some sequence alignment, and you look at this, right? So this tetracycline is fluorescent. So when you add an aptamer, you can see the fluorescence increase like 20-fold, right? So you immediately know it's working. And for this particular aptamer, so that's one of our favorite aptamers. We call it OPC5. That's the fifth most abundant aptamer. It has similar binding to all these three antibiotics, tetracycline, oxytetracycline, and doxycycline. They differ really just in this position with one or two hydroxy groups. So we believe its binding is probably on the top side of this molecule. Right? So that's the common part they have. Estradiol has been a very popular target for aptamer selection. So we obtained two aptamers that can bind to estradiol, so both are low nanomolar affinity. So we use this strand displacement reaction by labeling the aptamer with fluoride and the complementary strand with a quencher, right? So when we hybridize these two strands, the fluorescence is quenched. So when you add the target, aptamer binds, that will displace the quencher level strand, you get a fluorescence enhancement. So that's we can quickly obtain binding information. The green ITC is great, right? But it's too slow, right? So of these two aptamers, you can find, right? The first one can bind to the three analogs here, estradiol E2, and then estrone E1, and then this guy E2. The synthetic compound, right? That's the main component of this first chemical pair. So the first aptamer has the same affinity to all the three, so you kind of guess, right? So the binding is through this end of the molecule, and that's the common feature of all the three. And the second aptamer has no affinity to E2, right? Lower affinity with E1, and E2 has highest affinity. So it's probably binding through this end, right? So it's not high resolution structure, but you can have some guess, right, in terms of how things bind. So this molecule has been selected at least 6 times before us, right? So for DNA aptamer, we are probably number 7 selection, and there's also an RNA aptamer selection for it. So here we align all the reported aptamer sequence for this estradiol molecule. Our sequence don't align with any of them. So 5 of the selections use the full-length aptamer, so that's all about 70 to 80 merc, right? So only one that was truncated. So we again have no interest to test the full-length one too long, and so we just tested what literature reported truncated. So it's one here, and the third one here. So when we're doing ITC, yeah, we saw no binding for 2 of them, and the third one has weak binding, but 1 micromole Kd. Okay, so ATP and adenosine, right? So that's the classical aptamer. If you work with aptamer, you probably know I have used it before, right? So this is the 27 nucleotide, a very short aptamer, actually can bind to 2 adenosine molecules selected by the short stack group in 1995. So we just did it again. In this time, we used both adenosine and ATP as target for selection, and the consequence, the outcome of the 2 selections actually were very similar. So we got the same families of aptamers. So we doing deep sequencing of many different rounds, right? So we found that the aptamer actually comes out very fast. So at round 6, when the adenosine concentration was like 0.5 millimolar, right? So the majority of the library, we pretty much don't see anything else, right? So is this classical aptamer, this one. But when we're pushing the selection stringency by lowering the adenosine concentration, you can see that classical aptamer just goes down, right? Down to about 1% at round 13. But new aptamers, right? So 2 new aptamers, one is deployed 1301 and one 1304. These 2, right? So they start to dominate the library. This time we went down to 1 micromole, right? So ATP went down to 10 micromole, right? So it's still the same trend of the classical aptamer goes down and the new aptamers goes up. So now we have 2 new aptamers, both with about 200 nanomolar Kd for adenosine. So that's about 35-40-fold better than the classical aptamer. And the binding stoichiometry is different, right? So these 2 only bind to 1 adenosine instead of binding to 2. So we believe so this is actually more similar to the RNA aptamer for adenosine and ATP rather than the DNA aptamer. Theophylline is another compound, right? So that's famous in the aptamer field. When people say excellent selectivity for aptamers, right? They usually talk about this example. So this is the RNA aptamer with about 10,000-fold selectivity for theophylline, better than copain, right? So we use the theophylline as a target and copain as a counter target to do the selection. And the library is really interesting, highly converged. The top 20 sequences, that's about 75% of the library, is pretty much the same, right? So we divide into families, but look at the conserved sequence red and blue, they're just switch side, right? It's circular permutation. When you look at the secondary structure of the RNA aptamers and the RNA aptamers, very similar, right? Not exactly just the change T to U, but overall it's very similar. So we're now trying to do some more work to compare the RNA and the DNA aptamer in terms of how they bind. And from IDC, you can see, right, so nice binding with sulfurine, not with caffeine, theobromine, tyrosine, so these analogs. Then we again use the stranded displacement reaction to look for selectivity, right? So label fluorophore quencher, and we have the target, or you can see the nice concentration dependent fluorescence enhancement. And so you can see here that's our sulfurine, and we actually achieved about 250,000-fold selectivity for sulfurine compared to caffeine. The RNA aptamer is about 10,000-fold. We did not do RNA side by side. We just cited the literature value. I think part of the reason could be the RNA aptamer was selected by immobilization of the sulfurine molecule. Right? So we use free molecule. That could give us a bit of advantage there in terms of finding the actual target. Right? So in every compound we tested, it's more selective for our compound. And when we look at the relative selectivity, right? So this is 3-methyl-xanthine has the worst selectivity for the RNA aptamer and also for us, right? So I think that the way of binding should be really similar for these two kinds of aptamers. Yeah, lactate. So everyone telling me, right, lactate is important. So, but I was thinking, okay, can we actually get an aptamer for lactate? It's such a small molecule, right? So we tried it anyway, and actually it's not too bad. So we got these two types of aptamers. These two, right? Okay, it's a circular permutation of the sequence, same way of binding, and then there's another one that's not bind as good as this one. So these two aptamers, I think the affinity is about 400 microvolts, not great. But I think it's close to the physiological concentration of lactate. So lactate in our body is mostly air lactate, right? So it's also D-lactate. We don't really have it unless there's some, I guess, bacterial infection, right? So D-lactate. The selectivity for A and B is about 7-fold for our aptamer. And for some other compounds, right? So like this is 3-hydroxybutyrate has just an extra methylene group, has no binding. So yeah, it has got pretty good selectivity for air lactate. And we labeled the lactate aptamer with green fluorophore and also the glucose aptamer, which was not selected by us, which took from the literature, labeled that with the side 5 red fluorophore. Right? So mix them in the same solution, and so you can see here, right, when we add lactate, only the green fluorescence increase, we add glucose, red fluorescence increase, and we can do this in serum. Like this lactate actually works actually like at 90% human blood serum. So the binding, I mean, the fluorescence background is high, right? But you can still see the fluorescence increase when you add the target. Yeah, that's what I want to share with you. So we have been doing aptamer selections in the last 3 years also, and mostly with small molecules, and recently we're expanding to tissues. And I think library mobilization is a more general method and likely more reliable for small molecule targets. Right? And by doing deep sequencing, we actually can get more insights. So IDC and strand displacement, right, fluorescence assay are more reliable compared to using gold nanoparticles. So I think no one should use gold nanoparticles to validate aptamer binding. Right? So once you have to find the aptamer, you can probably simply using gold nanoparticles to make sensors. So that's my group. So those with the head circle, those are the aptamer selection members in my lab. Thank you.